use definition to find the area under the curve on this interval. So let's take a look. We have that the area is defined to be limit as n approaches infinity, sigma I from 1 to n, f evaluated at xi times delta of x, where the delta of x expresses the length of each of the small intervals in the subdivision, and then this xi represents the right endpoint of each of those small intervals. So in order to continue this calculation, we will need to find delta x as well as xi. So because we're working on the intervals like this, so we can follow the formula. Delta of x will be the length of this interval, b minus a, divided by n, which we can plug in to be 2 minus 1 divided by n. That comes to 1 over n. So we have length being 1 over n. And then we can find xi by using a plus I times the length of the small intervals. And that's going to be, a is going to be 1 plus I times 1 over n. Okay, so after we have delta x and then xi, we can plug these into the formula. And then we have sigma f of xi. So that will be 1 plus I divided by n raised to the power 3 according to the formula of f of x, and then delta of x is going to be 1 over n. So the rest of the work is just to calculate the limit of this expression. And because this expression has some sigma notation, so we will be using the formula on the left side to turn those summation into expressions in terms of n. So let's try to simplify this. We want to work on this cube, so we will be using the perfect cube formula, which is like this: a plus b bracket cube equals a cube plus 3a squared b plus 3a b squared plus b cube. Okay, using this formula to expand that cube, we will have limit, and then this is going to be 1 cube plus 3 times 1 square times I divided by n plus 3 times 1 times I divided by n squared plus I divided by n cubed times 1 over n. And then we will simplify this by distributing the sigma notation into the bracket, and at the same time I'm going to write this 1 over n here. So we have sigma of 1 plus sigma of this 3i divided by n plus sigma of is 3i squared divided by n squared plus sigma of I cube divided by n cube. Going to be like this. And we know the summation is with respect to the index I. So for everything else, we can just factor it out of the summation notation, which means I can factor 1 divided by n right out here, and then that will leave me with just I in the summation. And same thing for this, 3 divided by n squared can be treated as a constant to be factored out from this sigma notation. And then by doing all this, we will have limit, and then I from 1 to n, 1 plus 3 divided by n sigma of I plus I from 1 to n, 3 divided by n squared sigma of I squared plus 1 over n cubed sigma of I cubed. I'm doing all the factorization. And then next step, we will turn each of this into expression in terms of n by using the formula right here. So for example, this one, it turned into this, and then this one will be replaced with this, and then this one will be replaced with that. Just the formula for the first n term of consecutive integers, square of consecutive integers, and the cube of them. And then we're gonna have limit this 1 divided by n. This is adding n of these ones together, so we're gonna have n, simply n for this term. And then second term, this will be n times n plus 1 divided by 2 plus 3 divided by n squared. This is n times n plus 1, 2n plus 1 divided by 6 plus n cubed, n squared, n plus 1 squared divided by 4. And then we will have some simplification. Cancel, and then cancel this. Okay, and then this one we cancel this square with this cube. So we also we can distribute this n into the bracket, this 1 over n, and we can simplify the expression equals 1 plus this is 3 over 2 n plus 1 divided by n plus this 3 divided by 6 can be simplified to 1 over 2, and then this is gonna be this distributed to here will have n plus 1, 2n plus 1 divided by n squared, and then continue. We have this n multiplied with this, so that's n squared. So that's n plus 1 squared divided by n squared times this 1 over 4, like this. Okay, so almost done. You just evaluate the limit of each of the terms as n goes to infinity. We know very well about limit of a rational form as n goes to infinity. If the power of the numerator is the same as the power in the denominator, then we know that the limit is just the ratio of their leading coefficient. So for example, this one, right, n plus 1 divided by n, we have limit of this equals 1 as n goes to infinity. So we'll just simply replace this by 1. And then for this one, we take a look at the ratio of the leading coefficient. Leading coefficient here has 1 times 2, right? And then it's gonna make up the power 2, which is the same as the bottom. So we can expect that the limit of this as n approaches infinity is gonna take us to 1 times 2 divided by 1, which is 2. And this one obviously has the power on the top being 2, this is also 2, okay? And the leading coefficient is 1, 1. So limit of this one is going to be 1 as n approaches infinity. So keeping all this in mind, we will calculate, and that's going to be 1 plus 3 divided by 2 times 1, and then plus 1 over 2 divided times this, that is 2 over 1. That's the leading coefficient. And then this one is going to be 1 over 4. Okay, so and then calculating all the computation here is going to take us to 2 plus this, so that's going to be 2 plus 6 over 4 plus 1 over 4, which is going to be 8 plus 7, so 15 over 4 as our final answer.